Hi, my name is Giulio Alessandrini, and with my colleague Mikayel, we are going to present the latest addition in the field of OCR and facial analysis using our new neural network capabilities.
My name is Mikayel and Giulio. We work both in image and signal processing team, and we will be presenting to you what's new in the OCR and facial recognition aspects which are integrated and not yet into the Wolfram language.
So just one brief point. We are doing the talk together, so maybe let's get all the questions at the end because we don't have much time.
Yeah. All right, so I will be talking about the optical character recognition capabilities in the Wolfram language and the integration with neural networks to do some cool stuff. So just to give you some background, so we had text recognized since version 8. It has been changed a bit since that time, and the latest update was in 11.2. So what we added is basically now you have a way to specify the level and the property you want to extract. So we'll take a look what they are right now. So let's first see what the properties are. So one may specify now what to recognize, basically, to recognize the text or to get the bounding boxes or to get the strength of the recognition. So say in case of this image here, so I see that the strength of the recognition is pretty high, and we'll see this particular example in more details later on. And there is also level specification which can be specified to recognize the whole block, the word, line, character, and so on. So basically this is, in case of this image, we just recognize the text word by word, and this is pretty cool. All in all, you could come up with nice looking data sets which will describe your image in sense of what text is located where, and you could even extract the images of the text recognized per the level of the level that you specified. There are also some new options in there. One of them is something which is called recognition prior. So what recognition prior is it's something that to help the text recognized to understand what it's going to work with. So let's take a look at this example. So this looks like an M. Yeah, oh, sorry. Does it look better or a bit more? More. Better now? Okay. 3? Okay.
Don't push it.
Okay, so in case of this image, it's like from the first view, it seems to be a letter M. But actually, if we specify that we are interested to see what is it in a sense of being a character, we'll see that this is indeed M. But if we do not specify what it is, it will recognize it basically symbol by symbol. We can see that these are actually not connected between each other, and this is recognized as a Roman letter, so kind of. Another interesting new option is something called masking, which basically takes a region or regions in a form of image or actual rectangles to help text recognize to figure out where approximately the text is. So in case of this image, I specify that there is this mask where the white part is responsible for the region that there is a text in there, and to recognize, I see that yes, indeed, this is the stuff, and your mind is the text that is located in that part. So again, the kind of partial access to what we want to recognize. Last but not least, there is new thing in specifying languages. So pretty much it was like you could specify what language the text is and to try to recognize, but there was actually a problem because you could have different languages with different sets of alphabets where the characters are different. Now you could specify different languages at the same time to specify what languages are present in the image. And you can see that in this case we have like German, we have Russian, and we have Spanish, or it could be Italian, and the alphabets are different, like this Z is not present in different alphabets, and so on. So we can see that the recognition is taking the right language per text unit. Now, like to give you an idea what all these can be useful, I'll be presenting some applications, some of them toy applications, to show how can these be actually used in real examples. So say we have an image like this, which is a graphic, and we have some letters on it, which each of them is assigned to a point. Now, if we try to do a text recognize on these, we'll see that there is nothing recognized actually. But what we can do, we can use the thing with mask. We can basically try to specify a mask to help the text recognize to locate where the text is on the image. And that's basically it. And we know that per segment in the mask, we are interested in characters. So and we need to specify character as a recognition prior value. So let's try to do. So we have something. Let's see what it actually is. So what we got is we got that the text are located in these red bounding boxes, and if we hover, we will see the actual recognition, which is pretty accurate for this example, and the strength of the recognition. So this is kind of a toy example how the masks and recognition prior option can be useful. The next thing I would like to talk about is, as I said, we will be talking about the optical character recognition as well as the integration of neural networks into them. So say we have an image like this, and the text recognized is not initially trained to work on natural images. So again, if I try to recognize text from these images, like this London and Maverick here, we'll see that there is nothing happening over there. But I've imported a neural network, just a random one from just surfing, and it's pretty straightforward. And applying it on the image, I now try to figure out where the text is located on the image. This is kind of an automation of specifying the masking, which does it for you. So we now know that the text is located somewhere in here for the first image and here for the second image. Now we can take a look and see that indeed when we specify the location of the text, the recognition is significantly improved, and we get the bounding, highlighting, and the exact text that was written on the image. Another cool thing that we could do is to have an image like this, which is kind of a vocabulary screenshot from an internet, and now let's try to convert this to an actual Wolfram language representable table vocabulary. So what we do is, again, we need our network to try to extract the approximate position of the text on this image. And what it does is actually just finds the text and gives us a bounding box. So that's pretty much all we need for this type of examples. And we see that the text detection went pretty accurate. For some cases, it's not that accurate, but I mean, this is something that was never trained by us for a specific purpose. This is just a random network. Okay, now what we need to do is we need to basically differentiate the left column from the right column to figure out which word corresponds to the other word, which is basically the translation of the letter. And that's pretty straightforward to do. So basically, we know that the left column now is Russian and the right column is English. And what we can do now is just do the recognition stuff and recreate the Wolfram language table vocabulary, which is the almost accurate representation of the previous one. It's not like you can see that restaurant here is not super accurately detected, but again, there is there are ways to improve these things. Another thing that may interest some of you is that when you have a plot like this, we can actually try to recreate the plot contents and the plot skeleton into the Wolfram language. So what we do, we again just need to extract the positions where the text is located on the image, and this actually should be accurate enough not to misinterpret the plot curves as letters or as possible text. So we see in this example, this is kind of accurate enough for us to do the things. Now what we need to do is basically, as we did in example with vocabulary, we need to basically differentiate what are the axes and what are the labels and put everything in the correspondence. So this is, again, super straightforward to do. We'll see that the verticals are these, the horizontals are these, and labels are separated. So we now have all the bounding boxes that are interesting to us to be able to recreate the graphics. And we just do extract the ranges for the range for the axis, which is done using the text recognize stuff, and also the labels, which is done using the same thing. Now what we need to do is basically we need to figure out what are the graphic points, the actual points of the graphic on the image we have, and try to reproduce it on the plot. And we can see that this is pretty much accurate reproduction of the plot that we had in the image. So basically, text recognize was responsible to create the skeleton, and the classical image processing techniques were responsible to recreate the actual graphics on this plot. Last but not least, probably the most fun example, we could do something like having a tabular notation for music and make Wolfram language to play them actually. So again, what we do, we need now to to figure out where the text is located. But in this case, we'll not be using the neural network stuff. We'll be just using the classical image processing approaches. And we see that this image, now we have all the bounding boxes where the tabulations are located on the image. Now what we need to do, we need basically to recognize them, to see what exactly is written where, and to make it in a form so that we can feed it to our sound object. And just to show you how it looks. Okay, so this is something that we are going to feed to the sound object. This is not something meaningful to look at, but to have an idea what's going to happen there. And now,
volume up.
Yeah, and now we can just feed this to a sound object and to have actual Led Zeppelin playing. I'll just stop here not to play like 47 seconds, but the main idea behind is that when you have a tabular note, it's pretty straightforward and not that seriously hard problem to make it play in Wolfram language. I guess that's it on my side, and I'll let just Giulio to continue with the facial stuff.
In our built-in functionalities. So this stuff is not even in any build right now, I think, most of it at least. So again, like I'm starting from something that we used to have, and let's see how we can expand on that. So for example, you probably may be familiar with find faces. It's our face detector. Right now it's using like classical image processing to find faces. And so there's like much room of like not just improvement, but also like extra functionality that you can inject into functions like this. So like this is a kind of standard, like let's find where bounding box for faces are in the image. But why we this is experimental design, so don't look for it in any future release yet. It's not even approved. But why in principle we cannot do something like this? I mean, it's perfectly sensible. Like we just want faces related to a woman in the picture. So I just inject some like neural network knowledge into find faces, and this allows me to get exactly the answer I want. And this is basically the technology that's behind our face demo downstairs. And like I can expand this arbitrarily. Like the more networks I have, the more property I can deal with, the more richer the query space is. Like for example, give me just faces for people under the age of 20, and I just get the baby. So as I was saying, like the idea is to use like both internal stuff and like new neural network and new classifiers and like merge it all together. Some of this you can do already. For example, I think is Etienne, you are here. No, okay. Is this in 11.2? I think this facial thing is facial gender is in 11.2 stuff. Yes. Okay, so this you can do already with the latest build. So you can ask, for example, this is calling a neural network from within, and it's telling me, okay, this man is actually a man, and like these things are like built in a smart way into the language. So you can see that. They support like standard threading, like this is kind of standard evaluation. This is like multi-thread evaluation, it's faster. And they have these nice operator forms, and people always ask me, like, why do you want to use operator forms? Like, we have standard functions. It's because then you can like merge them very easily in other functions. For example, I love this group by function that allows you like kind of map reduce. So let's say I want now to just sort them by and group them by gender. I just provide the operator, and boom, it's done. So like this is like an automatic dataset creation with like injecting neural network capabilities into the language. So just talking a bit about future plans, like I'm working out to something like this, and this is not the final form again. The idea is to have kind of a hub for like different features. This will eventually grow the more I play with this. And right now we have like kind of standard stuff. You can get like age, you can get genders, certain landmarks, like where are the eyes, where the nose is. You can get like descriptors, and we plan to be like rich in this. And I'm going to show you in later examples like what you can do with this kind of stuff. For example, like this descriptor here, like I don't know who's familiar with like feature extraction. Like you have an object, in this case a face, and you want to do computation on that. But this is an image. I mean, for us it's very easy. For a computer, it's not as much. Like you want it to work on numbers, possibly meaningful numbers, and not always using the pixel of the image is the best for this. So what you want to do, we have already a feature extract function, and that is getting richer and richer. The idea is like you want to use like specialized features that contain semantic information of the object you are working with. So in this case, I scraped the internet for some. This is just a Google web search for a president face, like these two keywords. And this is meaning like some other symbol, some like weird stuff. But I mean, for the most part, they are faces of presidents. And if I use feature space plot, this is using the standard image feature extractor, which is basically trying to guess the appropriate manifold like to represent a natural image, but not just a face, like any image. So this is a rich structure. Maybe it's even too rich for this problem. So we see that like some like all the grayscale images are together. This black and white is here. Like there are like people with kind of background maybe on one side. Like there are already some semantic in here, but it's not like specific face semantic. So now I'm calling feature space plot again, but using again this is an operator. So it's like getting the descriptor from like my custom facial feature function. And you see that now, for example, like all the faces of Obama are clustered together in the same area of the feature space plot. Because I mean, this representation is way better at capturing face information. So it knows about like, oh, I mean, one person looks here or there is the same person. It's not a different image. It has a concept, like it has been trained on like multiple images of the same person. While maybe a standard classifier has just like a bunch of people, a bunch of mushrooms, a bunch of different things, but it's not like very learned in doing something like this. And once you have this, you can, but by the way, this is the code I use to scrape images if you want to do it yourself. Once you have this, you can create your own custom classifiers, for example. Like, let's say I want to, like here, I want scrape a bunch of Obama faces and like random president faces. And then like typical problem, I want to like learn what an Obama face look like and differentiate that from like standard faces. So here we don't have much time, so I use a super simple approach. I just reduce this to 2 dimensions to make it like nicely and representable. And you see the red dots are my data set of Obama faces, and the like thumbnails are the faces in the wild. And you already see that like if you are able to create a distribution of the red dots, you can then easily use that distribution to extract the Obama faces from the wild, working in the same space. So I do exactly that. I normalize a bit this, and I create like this is a standard normal distribution with the like 2, 3, 4, 5 sigma lines. And then I use this to filter the faces. I compute like the distance on the data set. And you get like this is a sigma parameter. And I'm going here from like 0.2 sigma to 3 sigma. You see that like 3 sigma gives like a bunch of nice group of Obama faces. And of course, like, this is a stupid example, but you can train this on like whatever thing you want. Just to show like very quickly another like set of features that you may want to play with. We have support for facial landmarks. So here I'm using particularly a slightly richer network that what I had in the container function before. This is defining like something like, forgot how many, like 20 so points for each phase. And when I had this, I can like build all kind of algorithms that are like sensitive to the like position of like specific facial features. Like I want to, from like building a snapshot filter to like doing I don't know, face obfuscation if you have to anonymize pictures, like more serious thing. And just to show very quickly an example of what you can do, I can use the neural network to get the feature, in this case the points, and then I can use standard image processing to define a spline interpolation between two functions. So I can do like this is a very crude face morphing. And again, with like standard image processing technique, I can merge like this nice girl and make it like sort of manlish equivalent, and this is a very bad man. As one direction or the other direction, this is pretty gross. And then in the demo here, I put some like you may see that these are pretty crude. I'm just like blurring a bit the mask, but you can use like some multi-resolution branding and create pyramids and do all kind of like standard image process technique. And like, so like these two fields are not really not talking to each other. Like there's much we can do, there's much we will do, and I hope there's much that you will be able to do with the instruments that we provide. Thank you. So any question for me or Mika? Come here.
Sorry? Well, but you probably could get more or less convenient results with what we have right now. Yeah, I think if you for your particular problem, you better use classifier. I guess, I mean, like text recognize is currently not intended to recognize any handwritings. It's intended to recognize any scanned or printed documents, and for the hand recognition, especially if you have like handwriting from one person, you probably would have to do additional training to kind of help text recognize to handle it. But I mean, this kind of stuff is planned to be in. Not today, not tomorrow, but we know about that, and it's in our plans.
What about recognizing printed math?
Well, math is absolutely different story. I mean, like for the example I showed with graphics, it's again like semi-math because you have some points and you have like letters assigned to them. But especially doing some math OCR is again not something text recognize is intended to do. It's not designed for that. I mean, but again, this is again something that is work in progress currently.
For this, we are looking into like customized neural networks in order to be able to like right now we are just at the beginning of our like image to text capability, and I mean it's a direction we want to work forward to, but yeah, it's very at the embryonal state right now. So I wouldn't advise you to use this to do your math OCR yet. Sure. Our plan is basically to expose every network we use, and some of them, like, while our framework is maturing as well. Like we push for, we want to use more networks, so like we push for improvements of the framework, and the new framework allows us to train new stuff. So like it's kind of a win-win thing between the framework and us. But the standard plan is to add you've seen that we have this net model object, and we want to expose there basically everything. So you will be able to get the trained network, the untrained network, and use PCs, do whatever you want. And there's also much improved, I mean, the framework has been evolving, and in the 11.3 prototype, there's much improvement in like network, like knitting, like cutting, merging, like is getting easier and easier. So hopefully that will address your needs. I don't know if we can take any more questions. Maybe one, maybe zero. Okay, thank you.